Okay, we have here today another integral. This one's from the Columbia Integration Bee 2025, number 14. We have the integral from 0 to 2 pi square root 1 minus sine squared x dx. Okay, I think I'll do the straightforward thing. First of all, we notice 1 minus sine squared x, that's the same thing as cosine squared x, but we're inside the square root. So when I rewrite it, we have the same integral, but now we just are integrating cosine x dx. But the integral of cosine, that's just going to be sine x evaluated from 0 to 2 pi. Plug it in, sine of 2 pi is 0, sine at 0 is 0. And so for my final solution on this, we just get 0. But unfortunately, I'm not a very good artist, and also the answer is wrong. So we're going to have to back that up. The problem we have is when I went from here to here, inside the square root, technically we always need absolute value here. There's a lot of cases where we get away with it and we can drop it, but this is not one of them. We're going all the way from 0 to 2 pi. We're going to have negative values in here. So to do it right, what we need to do is break it up into cases. When is it negative? When is it positive? But I actually kind of want to skip that just because I think I've got ways that I'd prefer, but you could just break it into like, I don't know, 4 integrals each quadrant and do it that way. Now, there are a couple different ways. One thing you could do is you could look at the graph, and from that, you can clearly see that you could kind of break it up into 4 pieces, and it just repeats. So you just need the area of one of those pieces, and then you can multiply by 4. I'm going to skip that as well, and instead we're going to use Queen's principle, just because I like to have an analytic method. It's not going to be any faster than the graph, but it's going to be just as fast as the graph. And both those, it takes like a second to analyze, as you'll see in a second. Okay, so for our Queen's principle over here to the right, we just have this easy formula. If f of 2a minus x, where 2a is going to be the bounds here, if this is true, then we can just kind of scrape the 2 off and bring it out front. Now, the reason I say it's a 1-second method is because when I do it, I just divide by 4 and bring a 4 out front. Of course, that's going to reduce to pi over 2. This just happens from applying this formula twice. Now, I can do that in 1 second, but the explanation, of course, if you want to get all into it, if you prove it out and everything, go into all the different cases, that's going to be a longer time. But just to do it in practice, like if you were on an integration bee, it's just like 1 second. The reason it works so nice here is because it's squared. And when you do, if our upper bound here is either 2 pi or pi supplementary angle formula with 2 pi, it's only going to change the value of the function by a plus or a minus. Well, if it's plus, it's not going to change at all. If it's minus, the minus sign is going to get fixed by this square here. So that's why you can just say with any trig functions, when you shift it by 2 pi or supplementary angle, a single pi, that's always going to work here. Do it twice, divide off the 4, bring the 4 out front. And what we have is 4 times the integral now from 0 to pi over 2. But doing that entirely solves the problem we had initially, because now we're always in the first quadrant, so we don't have to worry about absolute value. We can just go to this cosine x because all the values are going to be positive between 0 and pi over 2. So we just go ahead and integrate it, and we get sine x from 0 to pi over 2. Sine at 0 is nothing. Sine at pi over 2 is 1. Plugging in pi over 2, sine at pi over 2 is going to be just 1. And so for my final solution on it, we just get 4. Okay, there you go. Quick and easy one from Columbia 2025. Thanks everyone for watching. Have a good day.